get a gravitational wave, you know it's a gravitational wave, but it's a series of wiggles. What does that mean? It's not giving you an image of the source. So we need solutions to the Einstein equations for various possible sources, black hole collisions, that tell us what those wiggles look like, and so we can identify what's going on. So that's one thing. We need solutions to the field equations.
And the field equations, by the way, have just magically appeared behind you. So.
And look how simple they are.
Well, that's actually part of the question that I wanted to explore. I mean, it looks simple, but we physicists have this way of hiding complexity behind the symbols. And for this part, actually, I just want to take us through, because sometimes in these programs, you know, it is meant for the general person who just has an interest, but we'd like to sometimes do a little bit of the math. And if you don't like math, you can shut this part off. But let's just do a little tag team here. So this is the form of the Einstein equations. And if you're doing it a little bit more precisely, it has a few more symbols in it if you're not using the natural units that allow us to set certain terms to one. But even that, if we go a little bit further, is hiding this. So this is actually a more complete way of expressing the equations if we're now going to unpack the meaning of that first symbol, g mu nu. But then you look at that and you say, well, wait, what do all those individual symbols mean? This is called the scalar curvature, and that thing g is called the metric, and there's this little combination of them that gives you the scalar curvature. But wait, what does that really mean? Well, that's hiding this complexity right here, because we have this way of hiding the summation symbols within what we call the Einstein convention, using indices that contract in a particular way. So that's what that symbol means. And if you go a little bit further and ask yourself, what is the first term, r mu nu? That's the Ricci tensor, and it's given by this combination of stuff. But what's that new guy on the right-hand side? That's the Riemann curvature tensor. What does that equal to? Well, that's equal to this combination, where those gammas are known as the Christoffel symbols, and then you take those, and what are they equal to? Well, they're equal to a particular combination of the metric contracted with various derivatives of it. It's all just to tell you that this is kind of complicated. And the goal of the Einstein field equations, what all of this in some sense is about, is understanding that guy called G, which is the metric tensor. And just tell us quickly what that is, and I'll have a little visual that'll take us through that as well.
Right, so Einstein's theory is a theory about space and space-time is a geometric structure. And the metric tensor, in some sense, at every point in space-time, it's a generalization of the Pythagorean theorem.
So actually, you have not seen this before, but you were following exactly what I hoped you say.
Okay.
So you said the Pythagorean theorem, so why don't we just put that up here for the heck of it right now. So you got 2 points there, and take us through what you're seeing right here.
Right, so you want to know the distance between 2 points. So now in general relativity, it's not the distance between 2 points in space, it's the distance between two what we call events in space and time. And so what the metric does, so with Pythagoras' theorem, we know it's delta x squared plus delta y squared plus delta z squared.
Slow down, I'm trying to click and stay up with you. Here we are. There it is, right.
So that little formula there encodes the geometry of Euclidean space. Now, you can also write it in terms of a metric, and it's a relatively simple, straightforward metric. And what people long before Einstein's time, when they started looking at general geometries of curved surfaces, they would say, well, how do we describe, if we now have a surface that's got a complicated curvature, we want to generalize what Pythagoras did. This metric is a convenient mathematical way of doing it.
And here's one just example, just so people who are following the math can go along. Here's a curved shape, if you will, and the distance between the 2 points is no longer just delta x squared plus delta y squared square root, which is what we learned in junior high school, but rather is given by some unusually looking strange combination of delta x squared and delta y squared. And if you curve it a little bit differently, we learned that the distance between those 2 points might be given by this particular combination of delta x squared and delta y squared. And finally, just to get to what you're describing in the general case, we can have combinations that aren't even just delta x squared, delta y squared. We can have cross terms, like on the far right, delta x, delta y. And finally, to get to that object called G, the metric tensor, this is sort of a generalized version of the Pythagorean theorem where you're going to allow the surface to be curved. And that G thing there encodes the geometry that Frans is referring to, and Einstein gives us equations, those complicated equations that we saw before, where you can determine the shape of space-time if you understand the distribution of mass and energy.
Yeah, exactly right. And then,
Oh, thank you.